Photometric stereo is a computer vision task to recover surface normal map from images captured under different illumination. While its reconstruction accuracy, the photometric stereo method is generally recognized as difficult to use. One of the most obvious reasons is that data acquisition is very complicated. When using the most photometric stereo methods under directional lighting, we need to take images in a dark room, and often requires complicated lighting calibration. Though there are a few photometric stereo methods that can be used under natural illumination, all those methods cannot handle complex shapes and non-Lambertian materials. The goal of our work is to realize a single framework that can be applied regardless of the object's geometry, material, or lighting environment. For instance, we want to perform photometric stereo on images that are illuminated with a handheld light under a complex indoor natural lighting. Such a complex lighting environment cannot be handled by any existing method. In reality, when we actually apply the existing uncalibrated photometric stereo method for directional or natural lighting, the recovered surface normal maps do not seem to be correct. However, our universal photometric stereo network can recover a much more reasonable surface normal map like this. These are other results. All objects have very complex shapes and materials, yet are illuminated by complex spatially varying lighting. Despite this, our network is able to recover somewhat correct normal maps. So, why is it possible? We will explain our ideas. First of all, let us explain why existing photometric stereo methods only work in specific lighting conditions. Photometric stereo methods have two categories for lighting setup: calibrated and uncalibrated. The calibrated method gets the light source information in advance, while the uncalibrated method simultaneously recovers the normal map and the lighting information. As you can see, both methods assume the physical lighting model in advance, which bound the method to a specific lighting setup. To make our method general to arbitrary lighting conditions, we eliminate all the prior physical model assumptions. Concretely, we replace the physical lighting model in the uncalibrated method with a non-physically based lighting model, named global lighting contexts. Global lighting contexts are feature maps that have no physical meaning at all but are used in a similar way as physical lighting information. While physical lighting parameters such as lighting directions are assigned to each image, global lighting contexts are extracted for each pixel individually. In other words, the global lighting context at each pixel stores information about the local lighting environment. The main advantage of this is that spatially non-uniform illumination caused by cast shadows and interreflections can be modeled within this model. Based on GLC, our network is divided into two parts: GLC encoder and photometric stereo decoder. The former extracts the GLC from all images and an object mask, while the latter treats the acquired GLC as lighting information and applies the pixel-wise photometric stereo network. Please note that the encoder and decoder use different working resolutions. In particular, the former uses a predefined resolution lower than the input one, which is called the canonical resolution. The purpose of using this is to make the network's receptive field and memory usage constant independent of the input image size. More concretely, GLC encoder firstly crops the images and object mask and resizes them to the canonical resolution. Then, the image and mask crops are concatenated for each lighting condition and individually fed to the multi-scale image feature encoder. The naive transformer model is then applied pixelwisely to exchange feature information among different lighting conditions for each scale. Then, communicated multi-scale feature maps are fused using a feature pyramid network. Finally, a feature map with 1/4 of the canonical resolution is acquired for each input image, which is defined as the GLC. Our photometric stereo decoder treats GLC in a similar way as the light direction in a typical pixel-wise photometric stereo network. Specifically, the raw observations of a certain location at the input coordinate are picked, and the GLC corresponding to the location is also obtained by subsampling from the canonical scale. Raw observations and GLCs are concatenated and then passed to a pixel-wise photometric stereo network to predict the normal. Our network is trained on fully synthetic data using a path tracing renderer and commercial 3D assets, and no real data is used. Finally, we present some real results. For detailed experimental results, please refer to the paper. These images are taken with a combination of natural and nearby handheld light, which cannot be handled by any existing physically based models. As you can see, the proposed method has succeeded in recovering plausible shapes, although they are not perfect.